This video demonstrates the application of explicit model predictive control on a proton exchange membrane water electrolysis. In the fume hood is a PEM water electrolysis prototype. The electrolyzer uses electricity to produce hydrogen and oxygen from water. Though the reaction is endothermic, heat is generated in the electrolyzer during the process due to Joule heating effect. As you can see, thermocouples are used to measure the temperature of the water. The temperature measured is used to determine the temperature difference across the electrolyzer. This is in fact one of the key components of this demonstration, because if the heat generated in the electrolyzer is not controlled, it will damage the membrane of the electrolyzer. So water is not just a reactant, but is also a temperature control agent. The flow rate of the water determines the rate of heat removal from the electrolyzer. So our main objective is to develop and deploy a control strategy for the effective operation of this electrolyzer. The current is supplied using the power supply device, which you can see here. And the temperature data is acquired using a USB-TC device, which is a data acquisition device from measurement and computing. The device beside the USB-TC is the Mario device from National Instrument. It is used to acquire the voltage and current data from the sensors and also used to implement the control actions or the control strategy. The control strategy, which comprises various matrices and parameters, are stored in the Mario device. Here you can see the current and voltage sensors for measuring current and voltage. You can also see the red object, which is the motor driver or the actuator that acquires the control actions from the Mario device and implements it in the pump to control the water flow rate. The algorithm for applying the control strategy is implemented in LabVIEW. Here is the main LabVIEW visual instrument or VI for implementing the control strategy. It contains shared variables and sub-VIs. Here is a shared variable for temperature difference across the electrolyzer, which is measured every second. The measurements are also used to estimate the state using a Kalman filter. Inside the Kalman filter sub-VI, the MathScript node uses the Kalman filter algorithm to estimate the states of the system. The measurement and estimated data are used to form the parameter vector, which is sent to the Explicit MPC sub-VI. In the Explicit MPC sub-VI, the matrices are retrieved from where they are stored in the Mario, and the algorithm in the MathScript node is used to search for the critical region where the parameter vector resides. When the critical region is located, the second MathScript node calculates the control action using the respective matrices from the identified critical region. The control action is sent to the shared variable through a fail-safe mechanism that sets the flow rate of water at 5 grams per second if anything happens. The control action is implemented in another VI, which converts the flow rate value to a PWM value, which is then converted to the voltage value that is sent to the pump. The computer is used to visualize the results of this operation. The chart on the top left shows the current, and the top right chart shows the temperature difference across the electrolyzer, which is the control variable. It's also called the delta temperature. Also in that chart, you can see the set point for the temperature difference across the electrolyzer. The bottom right chart shows the control action, which is the water flow rate. As expected, the heat generation increases and the delta temperature increases too. The controller is turned on, so when the delta temperature reaches the set point, we see the control strategy changing the water flow rate to maintain the delta temperature at the set point. Even when the current is adjusted, the control still maintains the operation well. When the set point is changed, We also see the corresponding change in the control strategy to maintain that set point. This shows how effective the explicit MPC strategy is as regards meeting the desired control objective. In conclusion, we looked at the various parts of the PEM water electrolyzer prototype, and we saw how the explicit model predictive controller is embedded into the MyRio device and used to control the system. We also saw that the controller was able to maintain the set points of the temperature difference across the electrolyzer. At this point, I would like to thank you for listening, and hope to see you in the next video.